Hey there, Math Hoppers! In this video lesson, we are going to learn all about parent functions and how to transform the graphs of functions. So what are parent functions? Parent functions are the easiest or the simplest form for a family of functions. And the families of functions that we have learned up until this point are linear, quadratic, cubic, square root, maybe a few others. We're going to go over many more in this video. And knowing the parent function and the rules for transformations will make graphing something that seems very complicated super easy. So knowing your parent functions and immediately knowing what the parent function for any family of functions looks like is going to help you when graphing. Some of the common parent functions we've already seen, or actually we're going to see the parent functions now, but these are the family of functions that we already have seen. We have seen linear functions, and the parent function for a linear function is y equals x. The most basic form of a linear equation is y equals x, where the domain and range are all real numbers. And what that means is the domain goes from negative infinity to infinity, meaning I can put any real number into this equation for x, right? Y equals x. I can put any number into that. And I will get, for my range being all real numbers, my output also consists of all real numbers. And that makes sense. In this case, y does equal x. So whatever I put in for x, I am going to, in fact, get out for y. We have also seen quadratic functions. The parent function for a quadratic is y equals x squared. Again, the domain is all real numbers. You can put any value of x into this equation. There is no value that you cannot simply square. So negative infinity to infinity is the domain. Notice the range is limited. This parabola has a minimum value at 0, meaning the lowest output we're going to get is 0. Our range goes from 0 to infinity because you can get any number from 0 on up. Also notice infinity will always have a soft bracket. That means it's not included. You can't say infinity is included in my range because infinity is not a value. 0, however, is included, so you get a hard bracket. And it's included because, look, 0 is in fact one of the outputs you can get for this function. We have also looked at square root functions, where y equals the square root of x. Remember, the graph looks like this because the square root of x is limited to positive values of x. You cannot take a square root of a negative number and get a real number. So our domain goes from 0, but 0 is included, all the way through infinity. You can take the square root of 0, and in fact, when you do, you get 0 out. So our domain and range go from 0 to infinity, where 0 is included. We have learned absolute value functions. Remember, those are the functions that look like a V. Parent function is y equals the absolute value of x. Again, domain and range are values we've seen. The domain is all real numbers. You can put any number that you want into absolute value bars. So negative infinity to infinity is the domain. The range is limited from 0, where 0 is included, to infinity because, once again, the vertex is our minimum value and the lowest output we can get is 0. Remember, if you take the absolute value of something, you're talking about a distance. You will never get a negative value. We have seen exponential functions, where y equals 2 to the x power is the parent function. The domain is all real numbers. You can put absolutely any number you want in for x up in that exponent, but the range is limited to 0 to infinity, where this time 0 is not included. You will never get 0 when raising to a power, right? We have seen cubic functions. We haven't done a lot with them, but we should know that they exist. Y equals x cubed is our parent function. Domain and range, all real numbers, and that is what the graph looks like. We have also seen cube root functions, where y equals the cube root of x. Remember, the cube root is not limited to positive numbers. You can take the cube root of -8 and get -2. And the graph is not limited. Domain and range, negative infinity to infinity. Let's look at some functions, or parent functions, of the functions we will use in Algebra 2. The rational or inverse function is 1 over x, y equals 1 over x. Domain and range are in parts, and when we put up the graph, you will see why. The domain, or the input values, go from negative infinity all the way to 0, but not including 0, and then they continue again at 0, not including 0, all the way through infinity. So look at all these x values I can put in. I basically can put in everything except 0 because there is a vertical asymptote at 0. Also, 1 over 0, that's not a value. Remember, you cannot divide by 0. 1 over 0 is undefined. And my domain shows that. I can put any value in for x except 0. My range shows something very similar. I can get anything out of this function except 0. Notice I do not have a value of the graph here touching 0. So domain and range, negative infinity to 0, not including 0, and 0 to infinity, not including 0. And we will use logarithmic functions a lot in Algebra 2. So we have y equals log base 2 of x, where the domain goes from 0 to infinity, not including 0, and the range goes from negative infinity to infinity because we can get absolutely any value out from this function. Again, we're not going to do anything with those functions in this video. I just want to bring them to light since we will use them a lot this year. Let's look at vertical transformations. Vertical transformations, I think, are the easiest to comprehend. We have f of x plus c moves the function up c spaces, just like we would expect. So we have the graph of y equals x. The graph of y equals x plus 4, has shifted up 4 units. Okay, so this is y equals x plus 4. All of our outputs are shifted up 4 units. If we look at y equals the absolute value of x, and we say we want the absolute value of x plus 3, we will shift the entire graph up 3 units. Let's look at vertical transformations where we're not going up. If we have f of x minus c, we move the function down c spaces. So let's look at our parent function for quadratic, y equals x squared. If we look at y equals x squared minus 2, we have shifted the graph down 2 units. All of our outputs are what they used to be, minus 2. Looking at the cubic function, y equals x cubed is there on the left. Y equals x cubed minus 5 shifts the graph down 5 units. Now let's look at horizontal transformations. These are the ones that you really have to kind of memorize this rule because this rule will throw you for a loop when you first see it. Y equals the f of the quantity x plus k moves the function to the left k spaces. Yes, I said that correctly. Plus k moves it to the left k spaces. What? Are you telling me that plus k moves to the left and not to the right? I, in fact, am. Horizontal shifts move in the opposite direction of the sign. And there is a logical explanation using function notation and standard form, but let's just take it a step back and talk about a scenario where you're going to a party, and that party is represented by the function f of p, or the time that the party starts is represented by the function f of p, where p is what time the party starts. So let's say it starts at 8, then f of p equals 8. If we change the function to f of the quantity p plus 3 equals 8, now we have the party time plus 3 hours equals 8. Well, if the party time plus 3 hours equals 8, the party has to start at 5 because you've taken the start time plus 3 and gotten to 8. So we have subtracted 3 hours from the party's start time. Graphically speaking, 3 less is a move 3 to the left. So from here on out, let's remember that horizontal shifts move opposite the sign, and horizontal shifts are always within the bracket system. And the bracket system can be a square root, a cube root, a parenthesis, absolute value bars. Horizontal shifts move opposite the sign. All right, so let's take y equals x squared. It's something we're very familiar with. And let's look at the quantity y equals the quantity x plus 2 squared. Now think about this. If you were finding the vertex, you would say what makes x plus 2 0, and that would be negative 2. So it would make sense to you that this is shifted to the left too, because the vertex is going to be at negative 2, 0. Or you could remember our party example, and that horizontal shifts are opposite the sign. The quantity x plus 2 squared moves to the left 2 units. Let's look at y equals the square root of x. And now y equals the square root of x plus 5. That 2 would move it to the left 5 spaces. Let's look at the other type of horizontal transformation, f of x minus k. Well, if plus k moved to the left, minus k moves to the right, and in fact, it does. So the absolute value of x, if we change that to the absolute value of x minus 4, we shift the graph to the right 4 units. One more, y equals x cubed. If instead we look at y equals the quantity x minus 2 cubed, we move that entire graph to the right 2 units. All right, let's look at some vertical reflections. Let's get to something that we already understand. If we have negative, or negative 1 times, but negative f of x reflects the function over the x-axis. Remember, reflections are simply mirror images. In this case, imagine the graph being folded over the x-axis. So y equals 2 to the x looks just like the parent function for an exponential, but if we say y equals negative 2 to the x, then we have reflected that over the x-axis. Notice I started with exponential functions because this is one people mess up a lot, but it really should be second nature. Let's look at one we really do understand. Y equals x squared. We know that a is 1. We know that a positive 1 tells you that this opens up. We also know that y equals negative x squared means it opens down because a is negative 1. So this is something that kind of reinforces this rule, this vertical reflection rule. Now let's look at horizontal reflections. We don't see these as often, but we do need to know them. If we have f of negative x, we are going to reflect the function over the y-axis. Again, it is a mirror image, but we are going to fold over the y-axis this time. So instead of looking at a parent function, which I could do, I think this is easier to see if we look at something that's already shifted. So let's look at f of x equals the quantity x plus 5 cubed. Okay, so now let's look at f of negative x. We have reflected over the y-axis very clearly. All right, now let's look at vertical stretches or compressions. If we take k times f of x, we stretch or shrink the function vertically. I know this is a rule that gets confusing, but depending on whether k is a whole number or a fraction, tells us what type of result we get. And I always think whole number, you get skinnier, and fraction, you get wider or fatter, but let's try to put it in some mathematical terms. A vertical stretch is something that pulls the graph away from the x-axis, so you're getting skinnier. A vertical compression shrinks the graph towards the x-axis. It should not say towards the x-axis, so you're getting wider. So if k is greater than 1, you have that vertical stretch. Since each y-coordinate is being multiplied by a number larger than 1, that should kind of make sense. And if k is a fraction, then the graph has a vertical compression. And again, it's going towards that x-axis because you're multiplying by a number less than 1. Remember, if k is negative, you're just also going to include a reflection across the x-axis. So let's look at some of these. Here is f of x. So it's the absolute value parent function. Here is 4 times f of x. So y equals 4 times the absolute value of x. This is a vertical stretch away from the x-axis. It's 4 times as tall as the original function. And when I said when we multiply by a whole number we get skinnier, this is what I mean. We had 1, 1 as a point here, but now we're multiplying that output by 4. So instead of 1, 1, we have 1, 4. Instead of 2, 2, we have 2, 8. So we're getting much higher, much faster, making us skinnier. If we have 1/2 times f of x, so 1/2 times the absolute value of x, we are getting wider. We are being compressed towards the x-axis. It's half as tall as it used to be. Instead of 1, 1, we have 1, 1/2. It takes us twice as long to get to that same output. All right, let's look at horizontal stretches or compressions. This is when we have f of k times x. So the k is not being multiplied to the function, it's being multiplied inside to the x value. And that's going to stretch or shrink horizontally. A horizontal compression pulls the graph towards the y-axis, and a horizontal stretch shrinks the graph away from the y-axis. Again, we have rules, but they're flipped. If you have a whole number, the graph has a horizontal compression. If you have a fraction, it has a horizontal stretch away from the y-axis. Again, if k is negative, do everything you would normally do and then flip it over the y-axis. Let's look at some of these. So we have f of x, right? We have the parabola, y equals x squared. Now we have f of 3x. So we say this is compressed by a factor of 1/3 because it's as 1/3 as wide, or 1/3 as skinny as it used to be. Then we have f of 1/4 x. This is stretched by a factor of 4. It's 4 times as wide as it used to be. I know that's confusing because we will see a 1/4 x and then they will say it's stretched by a factor of 4 because it's 4 times as wide. Let's just put all of the rules that we've learned up there. We have f of x plus k minus k. Those are our vertical shifts up and down. We have our horizontal shifts here. Remember, these are away from or opposite the sign, so plus k is to the left and minus k is to the right. We have reflections over x, reflections over y. We have vertical stretches and horizontal stretches. Let's describe some transformations. Let's do some examples. So if we have f of x equals the quantity x minus 2 cubed plus 1, this is a cubic function that's been transformed. This is our horizontal move. Minus 2 or negative 2 means we're going to go opposite of the left directions. We're going to go to the right 2 and up 1. So what we say is we take that graph of the cubic function, the parent function, and we shift it to the right 2 units and up 1. Now we have f of x equals negative absolute value of x minus 4. Again, this negative on the outside will tell us to reflect it over the x-axis, and this will tell us shift it down 4 units. So the graph of y equals the absolute value of x, reflected over the x-axis and shifted down 4 units. Now we have f of x equals 3/4 x squared plus 2. Okay, so again, this is going to tell us it's a vertical stretch or compression. And remember, because it is a fraction less than 1, it is going to be a compression. And then we're going to move up 2. So the graph of y equals x squared, vertically compressed by a factor of 3/4, shifted up 2 units. Now let's look at one where you don't know the parent function. They just kind of put it in function notation. F of x equals negative 2g of 3x minus 5. So this has everything. It has the reflection, it has a vertical stretch or compression, it has a horizontal stretch or compression, and it has that vertical shift. So remember, the negative tells us reflected over x. 2 right here means we're going to have a vertical stretch by a factor of 2. This 3 on the inside tells us we have a horizontal compression by a factor of 1/3, and we move down 5 units. That is a whole lot to do to one graph. But knowing the rules and knowing the parent function, in this case, parent function didn't help us because we weren't given the parent function, but knowing those transformation rules will help you graph any type of function. Remember, you should be subscribed to our YouTube channel. If you're going through your homework or you're going through a quiz in this module and something just doesn't seem right or you don't know how to get the answer, send those to us and we will make a custom video solution for you. Until next time, Math Hoppers, take it easy.